You have no filter. Hey, Corky, don't try that at home, okay? Okay. There is this kinetic molecular theory that talks to explain what makes gases so unique. And there's some assumptions that we have to accept before we can move along. First of all, the gas is made up of tiny particles. And because of that, their gas density is very low. So remember, density is the mathematical equality of mass divided by the volume. Since there's a large volume and very small mass, very low density. Number two, that there's a huge amount of distance between particles. This goes along with the fact that they're not very dense. Obviously, there's a lot of space between them, most of which is empty space. The good news about that is that we can compress that gas quite easily. And as you can see there with the cylinders, it's very easy to have a large amount of gas in a very small space by compressing it. Third one is that there's this constant movement that particles have. They're always colliding with each other. And it's basically how they transport across and they diffuse, is that they can move between each other and get from one spot to another. Fourth one is that they don't attract each other, so that you'll never have a situation where well, that's actually another one. But they can fill any size canister that you end up having, and quite easily they are expanded and will flow. An example clinically is as we open up a gas cylinder, the gas evacuates from it. They have a whole lot of collisions, but the collisions are perfectly elastic, which means that there's no loss of energy in the process. Those collisions are the thing that actually exerts the pressure. So it's the constant movement of the particles as they're hitting each other and hitting the walls of the canister. You end up having gas pressure being created. Because they're moving constantly, they don't settle out to one spot or another. So in the gas cylinder, the pressure is the same no matter where you measure it. Kinetic energy is related to temperature. As you increase the temperature, you increase the kinetic energy. You increase the number of collisions in the process. So heating a gas increases the number or the molecules' movement. The more they move, the more they collide. The more they collide, the higher the pressure that you end up having. Cooling does exactly the opposite. This is why there's safety features built into gas cylinders, so that if they are in a fire, they will have a mechanism by which the pressure can be released before they explode. And this relationship between pressure and temperature is called Gay-Lussac's law. And we'll come back to visit that when we talk about gas laws. What?
I was going to ask you to repeat one more time, but we're going to go over it again.
Many times.
Never mind.
So, why can gases be compressed easily? One and two is correct. They have low densities. They have large spaces between. You can compress them quite easily. Which of the following is true regarding why a gas with an odor can travel? That sounds wrong. Can travel across a room. So if I were to open up a jar containing sulfur, with that nasty smell, rotten eggs, eventually would disperse itself throughout the room. And that's because A, they're in constant motion. Okay. All gas molecules eventually run out of energy and settle to the lowest surface. That's false. They don't settle at all. The pressure inside a compressed gas is greater at the bottom than at the top. That's false. Uniform throughout. And what will heating a gas do to its kinetic energy and molecular activity? It increases them both. And what about pressure? It increases it also. And whose law is that? Oh, no, that's Gay-Lussac's. All right, so let's take a look at what's going on in the atmosphere. It's kind of a review of Dalton's law here. But we know that the pressure, the term pressure, is talking about force per unit of surface area. So we're always going to have some measurement like pounds per square inch. That basically is talking about those molecules exerting pressure. When we put that pressure into a liquid, we talk about it as a tension. So technically, the dissolved amount of oxygen in the plasma is the oxygen tension in the plasma. We know what the fractional concentration is. It's a fraction expressed as a decimal. And we talked about the partial pressure being one gas in a gas mixture, what percentage of that is involved. Barometric pressure, we're going to consider whatever is here in the ambient environment. And 1 atmosphere is equal to 760 millimeters of mercury. That is a value that you should be aware of. And I think there's a couple of more of them we'll cross as we go along. Whenever the pressure is less than 760, we're going to consider that a hypobaric situation. Greater than 760, a hyperbaric. And we know about water vapor pressure. What's the partial pressure of water vapor? Damn, you're good. Must have had a good teacher. So we know that as we go up in altitude, our barometric pressure goes down. Same is true as you go down into the water. As you go down, the barometric pressure goes up. So it kind of goes hand in hand. In doing so, the partial pressure of any gas will also go down as you go in altitude. So really above sea level is a hypobaric condition, below sea level is a hyperbaric condition. Go ahead. Absolutely. Yeah, because Lake Michigan is at a higher altitude. So typically we express these values on the left there. That's at sea level. So any lake that's higher up is still going to have, as you go down, some drop in barometric pressure, but it's not going to be as significant as at sea level. Okay. You guys know how to calculate out, well, these are just giving the partial pressures of the various gases that we know about. They all make up 1 atmosphere. We know how to calculate a partial pressure by multiplying it by the fractional concentration. Whenever you have a hypobaric situation where the barometric pressure is less than 760, you end up having the partial pressure being less. We went through that before, and we know that the fractional concentration never changes. Okay. So as you get further and further up, gravitational pull becomes less and less. That's why our weight changes. The gas molecules become further apart, less dense, less collisions, less pressure. That's why the barometric pressure is less, because the gravitational pull is less. Do you guys have these answers?
Yes.
Okay, good. So we know all about them. Barometric pressure, as altitude increases, barometric pressure falls. Gas composition stays the same. Partial pressure exerted by each gas goes down, and hypobarism occurs at high altitudes. or hypoxemia, I should say. So there. So our cruising altitude is 30,000. Barometric pressure outside the plane is 226. FiO2 would be 0.21, and the PO2 would be 0.21 times that 226. This is why we apply some oxygen if we lose that barometric pressure, and that would be at PO2 that would be high enough to support life. And I'm not going to bore you with how to go through the calculation because you've already done that. Below sea level, we end up having a hyperbaric situation, where again the barometric pressure can rise quite significantly as we go down. Roughly for every 33 feet you go down, you gain another atmosphere. No, I said that wrong. You gain 2 atmospheres. You double it. As altitude decreases, barometric pressure goes up. Altitude decreases, the gas composition does not change. The partial pressure of each gas will go up. Hypoxemia is rare because the oxygen pressure is so high. What's that? Oh, you can figure them out. Come on, don't be a wimp. Jamie. Do you want me to go through them again? As altitude decreases, barometric pressure goes up. Concentration of any gas does not change. Partial pressure goes up. And the hypoxemia is rare because the oxygen partial pressure is so high. So why don't we just throw all the people who are sick into the deep ocean? They'd be fine. They'd probably be compressed from all the pressure. We do use hyperbaric therapy in medicine. Typically, if there's an oxygenation issue, we can just by putting them at 2 to 3 atmospheres, drive their partial pressure up higher. And you can actually get up to 6 atmospheres in these chambers. 2 different types of hyperbaric chambers that you should be aware of. One is called a fixed hyperbaric chamber, where the patient and the caregivers are inside, which means that the caregivers also have to be only allowed to stay in there for short periods of time, because that high of partial pressure for long periods of time can be harmful. And then there's the monoplace chamber, and if you remember back, Michael Jackson, he bought a monoplace chamber to sleep in. Why? It's a good question. Probably not so much burn patients, because you need to access them more so. A lot of times we use these for, I shouldn't say that. Potentially, yes. Wound healing, yes, definitely. Not I'm hedging a little bit on burns. Patients who need high amounts of oxygen. One of the I think we have them here. Yeah. We can use it for carbon monoxide poisoning, although usually just simple oxygen therapy will work. Definitely wound care for anaerobic bacteria, because if you put them in a high concentration of oxygen, it will reduce their effectiveness. And some other kinds of poisoning. Higher atmospheres are typically used for the bends. When a diver dives, if they come up too quickly, the nitrogen will actually bubble into the bloodstream. And it's called decompression sickness, and it can get to the point where you can get altered mental status, lose consciousness, and die. So it's very, very critical that you get them. What they basically need to do is repressurize them again and then slowly bring them back down so the nitrogen doesn't bubble into the bloodstream. Yeah. No, it's just that as you go down and as you dive deeper and deeper, the barometric pressure becomes less and less. I said that wrong. Barometric pressure becomes more and more. You got the idea. Whether it's the weight of the water, I'm not entirely sure. I mean, it really doesn't matter at that point. When you're coming up too quickly, it's not a good thing. We'll also use it at this level for something called air embolism, where if somebody was running an IV and inadvertently ran air into the bloodstream, that can be lethal also. So. It's not without its own complications, as we talked about. You can get a lot of trauma, especially to the ear, because the eardrum is not a very thick substance or structure. Those are just some of the complications of it. Claustrophobia, especially with the monoplace chambers, because you're in this box. Would not be good. And there's some stuff in Egan that you can take a peek at if you're so inclined about hyperbaric oxygen. And I think I'll stop there. Now, do you think they mean get a third free? Because if you buy 2 and get 3 free, I'm assuming they don't mean babies and children here.